Air Liquide is a global gas company. It's present in 70 countries around the world. It has 40,000 employees, and we do about 17 billion euros a year in revenue. As part of that company, Medal is a subsidiary that makes the Air Liquide membrane. The Medal membrane was a joint venture between Air Liquide and DuPont. DuPont has the most advanced fiber spinning processes in the world, and they perfected the art of spinning a composite hollow fiber. This hollow fiber allows you to separate gas very efficiently and cost effectively. So Air Liquide is now the full owner of the Medal subsidiary, and we make the most advanced fiber in the world. We have the most productive hollow fiber available on the marketplace, and that allows the customer to cost effectively separate gases on site, requiring no external energy and no moving parts. Every 737 produced today by Boeing in Washington has one of our membranes on board, and that's to inert the center wing tank of the fuel system of the airplane. Without that membrane on board operating correctly, there is a risk of an explosion that would be catastrophic. So our membrane inerts the center wing tank of that aircraft. We have membranes that inert the center wing tank of the F-22 Raptor, the most advanced fighter jet in the world, and the upcoming Joint Strike Fighter, which will be the most prolific new aircraft of the next decade. So the Medal membrane is present in all of the most important airframes in aerospace technology today. The fiber that goes into the F-22 Raptor is the fiber that's in this membrane here. It's the core of the same technology that we use every single day in all of our products. The membrane itself is very robust, it's a very simple design, and it can be used in a variety of environments. We actually supply hundreds of membranes for use offshore in the North Sea for Statoil, Norway's state-owned oil company. And that is one of the most harsh environments in the world, the North Sea in the wintertime in high seas. And our membranes have reliably operated in that environment for over 15 years. So we have a very robust design. The DuPont tradition carries over to the Medal design. DuPont has a very robust engineering design standards, and that carries over into all of Medal's designs. So we have very close ties to the DuPont R&D facilities. We also have the Air Liquide R&D facility for North America is about 15 minutes away from the Medal facility. So we work very closely with our own R&D to bring cutting-edge technologies to market. Yes, it was actually a lot of good fortune. Medal was just kind of trying to figure out a way to bring our products to market in India. So MVS contacted us for an inquiry, and then we started a relationship. And then it was a visit to your facility in India that solidified our decision to back MVS as the preferred or only supplier of our membranes in India. Our strategy, because we cannot build systems for everywhere in the United States or everywhere in the world, and we can't be everywhere all the time, is to partner with premium suppliers of nitrogen generation equipment, and as our products are a core piece of their offer. So MVS fits that bill as the leading provider of nitrogen generation equipment in India. It's a natural fit for Medal, the leading provider of membranes in the world, to partner with MVS to bring a premier system to the Indian market. The membrane itself is almost a direct replacement for the PSA beds. The pre-treatment, the compression, and the control of the purity and all of the P&ID logic controlling the entire system is very nearly the same. So our intention is to find OEMs who already have a competency making air pre-treatment and compression packages and PSAs, and partner with them if they're willing to offer a membrane as a complementary technology to already their core competency. So in that regard, MVS is the perfect partner for us. Well, there's a number of different differences between a membrane and a PSA. A PSA is very good at higher purities, above 99.9%. A membrane is more suited for a 99 to a 95% N2. A membrane can go up to 99.9, but the sweet spot of the membrane is more of 95% to 99% N2. Also at higher pressures, a membrane can go up to 350 psi, so it can go very high pressures, 24 bars. And so anything above a normal operating pressure of about 10 bars for a PSA, the membrane makes more sense because you don't need a booster compressor after the PSA generator. Also, a membrane is very scalable. If you need to scale up a membrane, you can just add more membranes and build a bigger membrane bank. Whereas if you have a PSA installed and you cannot scale it up without adding an entire new PSA. Also, a membrane, if one membrane goes bad, you can continue to operate with the rest of the membranes and not have a complete system failure. With a PSA, if a component goes bad, you're offline until you can fix that system to get it back up again. And lastly, there's a lot less moving parts in a membrane system. You literally just have to add compressed air and you start making nitrogen. Whereas PSA, there's a lot of extra energy you have to add to the system and a lot more moving parts to make a lot of nitrogen. So there's a lot of differences in the membrane that allow it to be more flexible and more robust than a PSA system. If you design and maintain the system correctly, you can expect at least 10 years of operation. We have systems that have been operating for over 17 years that they finally come to their first replacement cycle. So if you maintain the pre-treatment, the membrane should last 10 years or more. And it's all down to a well-designed system, which is where MVS comes into, and maintaining the pre-treatment, which is where the end user comes into. If you follow the instructions that MVS gives you, you should expect 10 years of life out of a membrane, and more. The membrane works through the principle of selective permeation of gases. Feed air is fed into the front of the membrane, and it travels down these hollow fibers, less than 100 microns in diameter. The gas flows down the hollow fiber tubes towards the end of the product gas where you get your desired purity of nitrogen. The oxygen will permeate this wall of the hollow fiber approximately 5 times faster than nitrogen. This difference in the rate of dissolve across the hollow fiber is the way at which we selectively separate the gases. We can adjust the flow rate, the pressure, and the temperature of the feed gas to achieve our desired purity and flow rate on the product side. So this fiber is the smallest in the world. It's a composite fiber with 2 different polymers, one on top of the other, arranged in a hollow fiber that is about the width of a human hair. We have the smallest fiber in the world, and that allows us to pack more fibers into a given inch of diameter than any membrane in the world. What that means to the end user is you need a smaller membrane to make the same amount of gas as any of our competitors. This saves on space, and it also saves you money. That's why Medal membranes are the most advanced in the world.